So valence electrons. Valence electrons are really important. What are valence electrons? For the main group element, the valence electrons are those in the highest principal energy level. So those are the electrons with the highest principal quantum number. And the group number for those main group elements corresponds to the number of valence electrons that element has. That's the group numbers with the A's after them. 1, 2, 3, 4. Electrons in the lower energy levels are called core electrons. So the valence electrons are on the outside, the core electrons are in the core, in the middle. And the number of valence electrons has a tremendous effect on the behavior of the elements, chemical and physical behavior. So one of the reasons for the periodic law and the recurrent properties is the number of valence electrons. So if we look at this partial periodic table, where we're looking at the first 3 rows, just the main group elements. These are group 1A elements. So they all have 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, 8 valence electrons. What we're showing here is the highest principal energy level part of the electron configuration. So lithium would be 1s2, 2s1, and that's the 1 valence electron. Over here for argon, we looked at argon on Monday. Argon, you could write its electron configuration as neon in brackets. So yeah, I can do that. Let's do that. Could write it like this: the previous noble gas, 3s2, 3p6. So these are the electrons that have the highest principal quantum number. Those are in the farthest, the largest orbitals, and those are the valence electrons. It kind of makes sense that the electrons on the outside of the atom are the ones that interact with other things. So the reason that oxygen and sulfur share some common chemical and physical properties is because they both have 6 valence electrons. The noble gases are very unreactive because, except for helium, they all have 8 valence electrons. And that's sort of a special situation. It makes them extra stable. Helium is one of the smallest, the second smallest element. It only has 2 valence electrons, but that's also a very stable place because that's the full level. This is not going well. It's okay. We'll just go on. Okay. Write an electron configuration for phosphorus. Identify the valence electrons and the core electrons. Okay, well, how many electrons does phosphorus have? It's got 15. Okay, so 15, we need to start with the first level. So we're starting with 1s. That first energy level has 1 orbital. It can hold 2 electrons, so we can put 2 electrons in there. And so that would be the first floor full in the hotel. And then we move up to the next floor. On the second floor, we've got 2 rooms, an S room, and the S room can hold 2 electrons. And we've got a P room, right, 2p. And the P room can hold how many electrons? 6. So we've got 10 electrons accounted for. We need to get to 15. So we're going to go up to the 3rd floor of the hotel. The 3S room can hold 2 electrons. So now we're up to 12 electrons. We need 3 more. So those are going to go in the 3p room. There'll be 3 of them in there. Everybody follow that? So that's the electron configuration for phosphorus. Identify the valence electrons and the core electrons. So what we're looking for is what's the highest floor in the hotel that has electrons on it? The 3rd floor. So these are the valence electrons. Sometimes I call them VE. And then these guys are the core electrons. Okay? So the valence electrons are the electrons staying on the highest floor of the hotel that anyone is staying on. There are, there's a fourth floor, but nobody's up there.
Does this mean that these electrons are in the same energy state as the
As the what?
As the same energy state?
Well, they are roughly at the same energy, but we talked about splitting and penetration, the interaction between the different electrons. So the S orbital is a little lower in energy than the P orbitals.
Why isn't it just 3?
Why isn't it just 3? That's a good question. Why isn't it just the highest energy orbitals? Well, that's a good question. That doesn't work with a lot of other things. I know that's not a very good answer. Yeah, that doesn't answer all the patterns and things that the highest principle level answers. Hopefully, after we get a little further, if you ask that question again, I'll be able to give you a better answer. Anybody else? Okay, so now I'm going to show you how we can get the order of orbital filling from the periodic table instead of having to memorize stuff. So we can divide the periodic table into 4 different blocks that represent the filling of the 4 different types of quantum shells, S, P, D, and F. And so in the hotel, that corresponds to the 4 different kinds of rooms, right? The group number for our main group element equals the number of valence electrons that element has. And the row number tells us the highest principal quantum number for that element. So the group number tells us how many people are staying in the highest floor of the hotel, and the period number tells us what that floor is. So if we look at phosphorus is in group 5A. It's got 5 valence electrons. It's in the 3rd period. Those electrons are in the 3rd principal energy level on the 3rd floor. Okay? So you can read that off the periodic table like you're reading a graph or something. So for fluorine is in group 7A, and it's in the 2nd period. So what's the highest floor in the hotel that has electrons? The 2nd floor. And how many are up there? 7. It's in row 2, group 7. 2nd floor, 7 electrons. 2nd principal energy shell, 7 valence electrons. Okay, so here's this beautiful, colorful periodic table. So these first 2 columns in blue represent S block filling. The pink over here is P, the yellow is D, and the green is F. So how many electrons can be in an S subshell? 2, right? Because there's only one orbital holds 2 electrons. How many columns are there here? 2. So the P subshell has 3 orbitals. The P room has 3 beds. How many electrons can hold? 6. How many columns are here? 6. D block. How many electrons can fit in the D subshell? 10. How many columns are there in the yellow? 10. How about green down here? 14. What? Isn't that trippy? It is and it isn't. The reason the periodic table has this weird shape that was originally arrived at by just looking at common properties, it has to do with how the electrons are structured within the atoms, because that's what affects the behavior of the atoms. But Mendeleev put this together. He didn't even know what electrons were. Quantum mechanics had not been invented yet. So here's how you can get the order. So the period corresponds to the principal quantum number. And so here this is 1, and we're filling the S block. And why is helium over there? Well, helium, like hydrogen, is one of those little baby brothers, and he just disobeys all the rules, and he gets away with it because he's small and cute, right? So he's over here for some other reasons, but there's 2. 1, 2. So that's 1s, 2, and then we're on the second floor. 2, and here's the S room, 1, 2, and then the P block, the P subshell, the P room, whatever you want to call it, filling up 6 electrons. So there's fluorine we just looked at. Fluorine has 2s2 and 2p5, total of 7 electrons, valence electrons. Next would be 3s, and there's 2 there, and we jump over here. This is 3p, and there's 6. We come over here, and there's 4s, and there's 2. Now this is where things get a little weird. So we've got this kind of a stair step going here. Doesn't it look like this next row should be up here? Right? This is how I think of it. It was up here, but it sank down. Kind of like the valley floor is sinking because the water table going down. This part sank. So this isn't 4D, this is 3D, because we think of it, it should have been up here, but now it's sunk. So 4s is lower in energy, so it fills first, and then 3d. So you fill up all the 3ds. Now we're back in the main block, main groups, and so this is 4p again, filling up, and then 5s, and this isn't 5d, it's 4d. Right? So for the D block elements, it's the period number minus 1. So we go across there, there's 4D, and then this is 5P. And now we get 6S. And again, this is sunk, so this one would be 5D. But you see that little gap there? And notice, this is 57, and that's 72. There's a bunch missing there. It's these guys. Now this periodic table on our wall is actually the way it's supposed to be. We don't show it that way on a piece of paper because it's too wide. Doesn't fit very well. Well, our limited space on the wall, the other way doesn't fit very well, so we literally took an X-Acto knife and cut the table and put it back together, and those elements there are actually another sunken place like this. So from 57, it goes over here to 58. So this is F, but this isn't, so this actually belongs in the 6th period, but that's not 6F. It's not 5F, it's 4F, because this is N minus 2. Oops. So for the F block, it's N minus 2, the period number minus 2. So you go through all of those, and then you come back here, and we're back to 5D, and then 6P, 7S, that 1 would be 6D, and then we jump down here. This is 5F filling up. 5F, and then back to 6D and 7P. And this is an older periodic table. We now have names for all of those guys. Okay, now the good news is I'm not going to test you on the weird stuff that gets in here, like why does one electron go into that d orbital before they start filling up the F? We don't have to worry about that. But you can get the order of filling from the periodic table. You don't need to memorize it. Any questions? For the valence electrons? So valence electrons are electrons in the highest principal energy level. So because these are sunk, if we look at titanium here, 3D2, those are actually on the 3rd floor of the hotel. It's only the ones on the 4th floor. the highest floor that are the valence electrons. So this one has 2 valence electrons. 2, this is weird, 1, 2, 2, 2. So those transition elements, most of them have 2 valence electrons. And that's part of why they're all so squirrely and unpredictable. Anybody else have any questions? Okay, so let's look at chlorine and how we can write electron configurations just from the periodic table. So here's chlorine. Chlorine is in row 3, period 7. So we can say, well, that's got 7 valence electrons. They're in the 3rd energy level. To write the noble gas configuration, of course, is the easiest. So here's chlorine. Go up 1 row to the end and find the previous noble gas. So that's neon. So neon. And then after neon, what do we have? We come over here. This is the 3rd row, the S block, 1, 2. So that's 3s2. And then we come over here. This is 3p. 1, 2, 3, 4, 5. 3p5. If you learn how to look at the periodic table, you don't even have to remember how many electrons are in the P, because you just count the columns. There's 6. That fills it up, and then you go on to S, and there's 2 there, and there's 10 in D and 14 in F. So let's do another one. Let's do iron. Do what? Do a harder one? Well, let's work up to it. Iron's hard to find in here because there are too many numbers. It's in the middle. It's 5. 1, 2, 3, 4, 5. I think it's this one right here. Did I count right? Yeah. So let's do iron. Well, what's the previous noble gas? Argon. So this is argon. So for iron, actually let's make a note of this. This is chlorine, and this is iron. So we're going to start with argon. And after argon, we've got 4s12. 4s2. And then this is D. Is it 4D? No, it's 3D, because it's sank, right? 3D, 1, 2, 3, 4, 5, 6. 3D6. That's not too hard, is it? Takes a little practice. You'll make some mistakes. But once you get the hang of it, it's like just so amazing. And that's not even all the cool stuff in the periodic table. The periodic table is like the 8th wonder of the world, if you ask me. Okay, you wanted to do a hard one. Yeah. You pick one. No, I'm serious. Do lead? Okay, so lead is down here in group 4. No, yeah, group 4, period 6. So finding it's hard. Okay, there's lead, right? So previous noble gas? Xenon. It really helps if you've got the element symbols in there. Okay, so we'll do lead. So xenon. And after xenon, we've got 6s2. And then this one doesn't show where the break is, does it? The break is right here. So we would do this 5D1, but we're not going to split up the 5Ds. So yeah, there's one there, but let's just jump directly to this. So this is 4F14. And then coming back, picking that guy up in the rest of these. That's 5D10 and 6P2. On an exam, I won't ask you to go past barium. Okay, I won't make you get into the F's. The F's are a little weird. There might be homework problems, but you can get help with homework problems, right? But on an exam, you should be able to do them up to barium. Right here, this guy. Okay, so you all feeling like you at least have an idea of what's happening here? It's a lot easier than memorizing stuff. It's all hiding right up there. It's been there the whole time. Okay, let's do bismuth. It's right next to lead. Let's do the full electron configuration, just to make it more interesting, okay? So here's bismuth, right? So just start at the top. So here's over there, that's 1s2, right? And then we come here, 2s2. We come over here, 2p6, 3s2, 3p6, 4s2, and then we've got these guys in here. That's down a floor. 3D10. If you don't remember the 10, count the boxes. This is back to 4. 4p6. And that's 5s2. And in here, 4d10. 4d10. 5p6, 6s2, I'm running out of space, 6s2, get rid of that, I don't know how that got there, and then this guy down here, so that's not in group 6 or 5, that's actually 4, 4f14, back up to catch these guys, 5d10, and 1, 2, 3, 6p3. That's why we use the noble gas shorthand, because it's so much shorter. And why do we need to do this over and over and over again? Well, after a while, you just remember it. You don't even have to look at the periodic table.
So the valence electrons would start 6s2.
Yeah, so good question. What about the valence electrons here? So we're looking for the highest principal quantum number. We've got 1s and 2s and 3s and 4s and 5s and 6s. So it's the 6 ones.
Oh, it's only those.
It's only the 6s. So valence electrons are not the electrons in the highest energy orbitals. They are in the highest principal energy level. So this is where the hotel is a little easier. The electrons staying on the highest floor. So these electrons are staying on the 6th floor. These electrons are on the 6th floor. So those guys count. There's 5 of them up there. There's a bunch of electrons here, and they're paying more for their room than these guys, but that doesn't matter. They're not on the highest floor of the hotel. The valence electrons are the ones on the highest floor. Okay? That was an excellent question. Anybody else? Yes?
So the 6s and 6p are actually in the 4f.
These are in a higher principal energy level. So the principal energy level is the quantum number. That principal quantum number. In general, the orbitals in a higher principal quantum number have higher energy, but because of the penetration and the splitting and the shielding and stuff, these 5d orbitals are actually higher in energy than the 6s.
So you use electrons
Excellent question. What happens when you lose an electron? They will come off the last filled orbitals first, for the most part. That does get a little complicated. Anybody else? Write electron configurations for each element. Let's do the noble gas ones. So for chlorine, what's the previous noble gas? Neon. And after neon comes what? 3s2, 3p, 1, 2, 3, 4, 5, right? 3p5. So silicon, previous noble gas, also neon. And then 3s2 and 3p2. You seeing that okay? Strontium. Strontium's way down over there. So in the 5th period, we go up to the 4th period and follow it all the way over to the end. Krypton, right? So krypton is the previous noble gas. And after krypton, we're in row 5. That first two blocks there, that's 5s2. And oxygen. Let's do the whole thing for oxygen because it's pretty small. So that first row is 1s2, 2s2, and then we're in the 2p block over there, and it's 1, 2, 3, 4. 2p4. When you write electron configurations, one way you can check yourself is add up the superscripts. 2 plus 2 is 4 plus 4 is 8. Oxygen is element number 8. It's got 8 electrons. For strontium here, we look at krypton and say, well, krypton has 36 electrons, plus 2 more is 38, and that's the number for strontium. Any questions? Of course, it couldn't all be quite that straightforward. There are some irregular electron configurations. So there's splitting because of the penetration and the shielding. So the 4s sublevel is lower in energy than the 3d, but the 4s fills first. But the difference in energy there is not very large. It's actually pretty small. So some of those transition elements have irregular electron configurations in which that s orbital either doesn't fill or half fills, and yet we have d electrons in there. So in the hotel, this would be like they're running some Groupon special or something, where if you meet these specific conditions, you get a break, right? These electron configurations must be found experimentally. There's not really any predicting them. So here are some of them. So for chromium, what we expect is argon 4s2 3d4. Reading it off the periodic table, that's what we would come up with. But experimentally, we have observed that it's argon 4s1 3d5. So what is going on there? Well, let me draw you an orbital diagram just for the stuff after argon. So this is 4s and this is 3d. Now let's use the bright red. So what we expect is that we put 2 electrons in there, and then we've got 4 more, and we put them in here like this. That's what we expect. That's what's following the pattern. But if this guy moves over here, isn't that beautifully symmetrical? Everybody has their own bed. Well, that's worth paying a little extra for, right? It turns out that there is a lowering of energy if you have exactly half full subshells. So now the 3D is half full and the 4s is half full. Now the next one after chromium is manganese. The next electron coming in would go into this 4s, and then things would proceed normally until we get to copper. So copper, we expect, would be like this, 4s2, 3d9. But that's not very pleasing, right? This is one awkward thing. If this electron moves over here, I mean, he doesn't care. He's sharing a bed anyway, right? Now this one is half full, and this one is completely full. And you get there's a coupon that you save money if you do that. So they did that, okay? It's not the scientific explanation, but hey, if it helps you remember it, that's all I care about at this point. You get to PChem and they'll do the rest of it. So we see some similar things, but not quite as nice for things like molybdenum, ruthenium, and palladium. So molybdenum is doing a similar thing to chromium, where it is taking one of the electrons from the s and moving it up to the d, so that both of these are half full. This one, I got no explanation for why it does that. 4d7, how does that help? Why did they make a special out of that? I don't know. It's there. This one, 5s2, 4d8. Okay, so what happens here is these two go up there, and then we've got a completely empty and a completely full. That kind of makes a little sense. Okay, so you need to remember just these first two. So if I ask you to write an electron configuration for chromium or for copper, you need to remember that it's a little bit irregular. Okay? I won't ask you about any of the other irregular ones, just these first two. Okay?